Okay, so section 3.3 deals with orthogonality. When are two vectors orthogonal? When the angle between them is 90 degrees. Now, if we go back to our formula for the cosine of an angle between two vectors. Now, the cosine of an angle between two vectors, we know there's a formula for that. It's the dot product between the two vectors divided by the product of the norms of the two vectors. Now, if the angle between two vectors is 90 degrees, cosine of 90 degrees is going to be 0. So that'll imply that the dot product between the two vectors will be 0. A non-empty set of vectors is called an orthogonal set if all pairs of distinct vectors in the set are orthogonal. And an orthogonal set of unit vectors is called an orthonormal set. Okay, let's look at that example. There U, V, and W are defined. Now, is U orthogonal to V? Well, look at the dot product. That is 1 times 2 plus minus a half times 4 plus 0. And that clearly is 0. So U and V are orthogonal. All right, number 2 is that set there, orthogonal set. So check all the vectors. U is orthogonal to V. The dot product between U and V is 0. The dot product between V and W is 0. And the dot product between U and W is 0. So all those vectors, every pair of vector in that set is orthogonal. And because every pair of vectors is orthogonal, it's an orthogonal set. The last one, is it an orthonormal set? For it to be orthonormal, we need every vector to have a norm of 1. Now, if you look at W and you work W's norm out, the vector W has norm 3, which is, obviously it's not a unit vector, so that's not an orthonormal set. Okay, next we have just a few definitions. So we're going to look at lines and planes, points, and normals. Okay, so again, guys, you know what a plane is. A plane in R3 is just a flat surface that extends in all directions. Okay, we know what a plane is. So just this quick definition, a normal vector to a line. So a normal vector to a line or plane, right, is a non-zero vector that is orthogonal to any vector joining 2 points on the line or the plane. Alright, so there, if you have a straight line, this vector n is going to be normal. It is perpendicular. It's orthogonal to any vector joining 2 points on the line. So basically, if you have a point there and you have a point there, and you look at the vector joining those 2 points, right, which is that vector there, call that vector u. You can clearly see that u's dot product with n is going to be 0. Okay. And then in a plane again, if you look at any 2 points there on the plane, and you look at the vector joining those 2 points, then a normal vector is the vector that is always going to be orthogonal to any such vector joining 2 points there. Right, next we have Theorem 1. Now, Theorem 1 is a way of finding equation of a straight line using vectors. So how do we use vectors to find equations of straight lines? So you take a point on the straight line, a fixed point, call it P, x0, y0, P0. And this is a fixed point on the line, on a line in R2. And now you also have the normal vector. Now the normal vector, this vector is normal to the line. What does it mean for a vector to be normal to a line? It means it's perpendicular to that line. It's perpendicular to that line. Now, to find the equation of a straight line, you want to find all points that lie on the straight line. So you pick an arbitrary point P, x, y, that lies on the straight line, and you want this point P to satisfy the following. What you want is you want to take the vector that has a starting point P0 and end point P. And what vector are you actually calculating? You're calculating this vector here. Now you want that vector, right? You want that vector to be perpendicular. You want that vector to be perpendicular to that normal vector. Okay? So what you want is when are two vectors perpendicular? When they have dot product equals to 0. So you want that dot product to be 0. So you want to find an x and a y that satisfies this equation, right? So that is the same as saying that this, which is the dot product, that there is the dot product. It's this dot product here. Okay, that is equal to 0, and that will give you the equation of the straight line. That will give you the equation of the straight line. So if we were to draw this, you basically have your straight line there, and you pick a point. Starting point P0, and now we want to and you're also given the normal vector. Now this is a vector that's perpendicular to your straight line, so that's the normal vector. Okay, and now you take an arbitrary point P, X, Y. It doesn't matter where you pick this point P. It could be any point. You just want this vector here, that vector, which is the vector that starts at P0 and ends at P. You just want that, you want that vector to be perpendicular to the normal vector. So in mathematical terms, if you were to write that down, you want this vector's dot product with n to be 0. And any x and y that satisfies this dot product there is going to be a point on the straight line. It's going to be a point on a straight line. So you can do this for any point, right? You just want all these vectors to be perpendicular to the normal vector. And once a point satisfies that, it is on the straight line. Okay, next we have Theorem 2, which gives us the ability to calculate the equation of a plane. So again, it's the same type of argument that you use. You pick a point on the plane, x0, y0, z0, so it's a fixed point on a plane in R3. And then you have the normal vector, which is the vector that is perpendicular to the plane. So just like you did with a straight line, you do with a plane. So that's a vector that is normal to the plane. So it means the vector n is perpendicular to the plane. Now, how do you find a point on a plane? So it needs to be a point x, y, z, where again what you do is you want to find all x, y's, and z's such that if you take the vector with starting point P0 and the vector that is endpoint P, if you take that vector P0P, okay, you want the dot product of that vector there to be equal to 0. Okay, so you want to find the x, y's, and z's that satisfy this dot product, which is then equivalent to basically writing that equation down, being equal to 0. Okay, so remember now that the vector, if you look at remember that this vector P0P is the vector x minus x0, y minus y0, and z minus z0. Okay, right, so we get the equation of the plane. So if you were to draw that again, so here you've got your plane. Okay, it's only a section of the plane that I'm drawing here. And there you've got your point P, 0. Okay, so there's P0. It's x0, y0, z0. And you have the normal vector, which is the vector that is perpendicular to the plane. And that's the vector n. Right. Okay. Now you want to look at points there. You want to be able to pick any arbitrary point there. Call that point P. Okay. And you want to look at the vector that lies on that plane there. And that is the vector P0, P. Okay. Now you want all x's, y's, and z's such that if you work the vector P0P out, the dot product of P0P with the normal vector is going to be 0. And any x, y, z that satisfies this equation is going to be a point on the plane. You can do it for all points on the plane. You can look at all those vectors there. Any point. All those vectors, they all need to have a dot product of n with a dot product of 0 with the normal vector n. And as soon as an x, y, z satisfies that, it is going to be a point on the plane. Okay, let's quickly look at those examples. So the first example there is here you've got the normal vector. Let's call that n, the normal vector. And that's the vector 1 minus 2. Okay, and you want the equation of the line through that point 1, 0 with the normal vector. So what you want to do is you want to find, basically that point there is your starting or initial point, and you want to find all x's, all your x's, such that if we call that point P and that point Q, right, so you want to find every point that's going to lie on that straight line and that is orthogonal to this vector n are going to, so you're looking at all vectors that are going to be of the form QP x minus 1, y minus 0, which is x minus 1, y. Okay? And you want all the vectors, such vectors, that are going to be orthogonal to this normal vector here. Okay, so that is basically what you want is you want all x's and y's that if I take the dot product of these vectors QP with n, it's going to be 0. So that will then give me the straight line, which is going to be x minus 1 plus minus 2 y is equal to 0. So that's going to be the straight line. And as long as you remember this formula or this way of thinking, you cannot go wrong. So that's the first one. Okay, let's look at the second one. So there's the point. We are again given the normal vector. Right, so that's my normal vector. And that's the vector 2, 1, 3. Now the points on the plane through that point minus 1, 2, 1. So there we have our point Q, which is the point minus 1, 2, 1. So we basically want we want all points x, y, z. Okay, call that point P. Okay, so so what we want is we want all the points x, y, z, such that if I work this vector out, the vector QP, right, which we know is x plus 1, y minus 2, z minus 1, such that these QP vectors are determined by the points x, y, and z. You want that vector to be orthogonal to the normal vector, okay, which is then going to give you all your points x that are going to have this property. In other words, it's all points x, y, z that are going to lie on the plane. Okay, so that is then going to just give me x plus 1 multiplied by 2 plus y minus 2 plus 3z minus 1 is equal to 0, which is then going to imply that my plane looks as follows. It's 2x plus y plus 3z is equal to 2 minus 2, which is 0, minus 3. You take it to the other side and you get 3. So that's the equation of the plane. It's the equation of the plane through this point x, y, z. Okay, so the last question asked me, what is the geometric relationship between those two planes? So let's look at the first plane, right? So the first plane, which is given as minus 3x plus 2y minus z is equal to 4. Now, if we go and analyze this plane, the normal vector to this plane is given by the vector minus 3, 2, minus 1. So what is this normal vector? This normal vector is a vector that is basically orthogonal to every vector that lies on the plane. And let's call this plane P and call that plane Q. All right. So that's for the plane P. So that's the normal vector for the plane P. Now, if we look at the plane Q, which is 6x minus 4y plus 2z. Okay, this is equivalent to the plane. I'm going to divide through by minus 2. So I'm going to get minus 3x plus 2y minus z is equal to 3 over minus 2. Okay, so the plane P and Q, they're equivalent to one another. And what is the normal vector? Just to avoid confusion, let's call that normal vector of P and normal vector of Q. Okay, the normal vector of Q is the same vector. Okay, now what does this imply? The vector that's orthogonal to every vector that lies on the plane Q is the same as the vector that's orthogonal to every vector that lies on the plane P. So what does that imply? If the normal vectors of two planes are the same, it essentially means what? It means the two planes have to be parallel. Because if this is the plane P, okay, there's the section of the plane P, okay, and for argument's sake, there's the plane Q, okay. Now we've got this normal vector here, which is NP. There's the normal vector NP, okay, and there's the vector NQ. Okay, now compare these two vectors. You see, every NQ is orthogonal to every vector that lies on the plane Q. And NP is orthogonal to every vector that lies on the plane P. So what this means, these two vectors point in the same direction. That vector is exactly the same as that vector, pointed both in the same direction. So that means the only geometric interpretation that I have for this is that these two planes have to be parallel. So okay, so as NQ is the same as NP, okay, as that is true, planes P and Q are parallel. Okay, so that's the geometric interpretation. Okay, let's look at the projection theorem. So the projection theorem's got some very nice applications, specifically calculating distances between points. So how does it work? So what we are given here is we're given the vector u, and now the question becomes the following. So there's the vector u. All right, and the vector w is given. There's the vector w. Okay, now the question here is, if we look at the vector u, now we know by the parallelogram method, we know that the vector u can be expressed there as actually the sum between vectors w1 and w2. Okay, and w2 is basically it's this vector. Okay, so that's w2, and w1 is basically going to be, it's going to be that vector there, w1. Now if you inspect, you'll see that the vector w1, which is that vector there, points in the same direction as the vector w. So that means that w1 is in fact a scalar multiple of the vector w. So we can find a scalar, let's call it k, such that w1 is a scalar multiple, that scalar multiple of w. Okay, now the question now is we want to find the vector w1. We want to go and work out what it is. So essentially what we want is we want to find a value for the scalar. We want to find a value for the scalar. So what we can also say is the following. We can say that the vector w, okay, the dot product of the vector w with the vector w2, w1, is 0. Okay, and why is this the case? Because you'll see here, those two vectors there are basically they're orthogonal to one another. And orthogonal vectors, the dot product between orthogonal vectors is 0. So now from there, okay, what we can say is that that's going to imply that w1's dot product with w2, like I said, is 0. But what is w2 in actual fact equal to? Remember, w2 and w1, if you add them together, you get u. So we can solve for w2 basically as the vector u minus the vector w1. Okay? And that has to be 0. So this is going to imply that applying the dot product rules we did in section 3.2, you then have the dot product of W1 with U minus the dot product of W1 with itself is equal to 0. So we can now go and continue in this fashion. So if we continue the dot product of W1 with U, okay, minus the dot product of W1 with itself, okay, so what is W1's dot product with itself? This is going to be W1 dot product with U minus, now what is the dot product of a vector with itself? It's basically the norm of the vector squared. Okay, now remember we said that W1 is a scalar multiple of W. So W1 is a scalar multiple of W. So K W is in fact W1. Okay, so there you've got the norm of that squared. So you've got that whole term squared equals to 0. And what is that term? That term is basically KW. Okay, now guys, you have to remember your norm rules from section 3.2. So that then becomes scalar multiple dot with U. Now what is that? That is going to be the absolute value of K multiplied by the norm of W, everything squared, okay, and from that we have then that holds, okay, and so that's going to be basically K squared multiplied by W's norm squared is equal to 0, and from here either K is 0 or we can go and solve for K as basically the dot product between W and U divided by the norm of W squared. Okay, so now we've basically solved everything. So we can now say that W1 we said is scalar multiple, which is K, and we're interested in this value for K. Okay, norm squared multiplied by the vector W, and this is also called what? It's called the projection. What vector am I projecting? I'm projecting the vector U, and I'm projecting it onto the vector W. Now remember, go back to your sketch here. There's W and there's U. So I'm taking U and I'm projecting it basically onto that vector there. So that's called the projection of U onto W, and I can also then solve for W2. Okay, sorry, that needs to be a bar there. Now W2 we said is U minus W1, and what is W1? W1 is the projection of U onto W. Okay, which is then basically, yeah, it's basically that vector there. Okay, so that's the projection theorem. Alright, so having proved that projection theorem, if U and W are non-zero vectors, then remember the W1 vector that we worked out, which is the scalar multiple of the W vector. That is the projection of U onto W. It's an orthogonal projection. And then the vector W2 that we worked out, that is the vector U minus the vector W1, which is where W1 is the projection of U onto W, the orthogonal projection. Okay, let's look at the last example. So we're asked to determine the orthogonal projection of U onto W and the vector component of U orthogonal to W. So we've got the vector U there, okay, and then we've got the vector W. And what we asked is, we asked to orthogonally project U onto W. So that vector there is that vector W1 we looked at in the proof. That's the orthogonal projection. And then we also looking at the component that is of U that's orthogonal to W, which is this vector here. That's W2. Okay, so we know W1 is equal to the projection of the vector U onto the vector W, and we know that that is the dot product of U with W divided by the norm of W, the norm of W squared. Okay. Let me just write that neatly. The norm of W squared multiplied by the vector W. So now doing that, that is the dot product of the vector U with the vector -1, and then you're going to divide that with the norm of W squared. Now the norm of W squared is 1 squared plus 0 squared plus -1 squared, multiplied by the vector W, which is 1, 0, -1, and that is equal to, if you go and dot product, you find that that is 1 plus -3, which is -2, okay, divided by 2, multiplied by 1, 0, -1. And that is the vector -1, 0, 1. Okay, now W2 we know from the proof of the projection theorem, that is U minus W1. So that is going to be U, which in this case is 1, 2, 3, minus the vector -1, 0, 1. And that's going to be the vector 2, 2, 2. All right, so there are the two vectors, the projection, the x and the y component of U. Okay, so let's look at a nice application of the projection theorem. So we're given an example there, and we're given a point x1, y1, z1, and we're given the plane P, and we're asked to find the distance between the point Q and the plane P. Right, so now remember, if we go back to the equation of a plane, we can find a point x0, y0, z0 such that you've got the following, right? So you have the normal vector, which is in this case A plus B plus C. Okay, all right, for the plane P. Okay, so remember that's the actual equation of the plane P. So now what we're interested in is the distance between the plane P and the plane Q. So what we have here is if we look at the plane, let's just draw a hypothetical plane there. Okay. And let's just do that. Okay, we've got the plane there. Now we've got the point more or less there. Let's call that Q, and Q is the point x1, y1, z1. All right, and then we've got this somewhere on this plane here. We've got that point, the point x0. Call that the point x0, y0, z0. Okay, and we want to find the distance between the plane P, that's the plane P, and the point Q. So let's look at this vector here. Okay, the vector with initial starting point x0, y0, z0, and end point x1, y1, z1. Now what we also have is we've got this normal vector here, okay, and the normal vector is the vector A, B, C, okay. This is from the equation of a plane. Now what I want to find the distance between this point here, the point Q, and the plane P. So what am I actually interested in? If I go up there until I get to that level there, what is it essentially that I'm looking? What is it essentially that I want? I want to find that vector. I want to find that whole vector there, okay? And that vector is this vector here. I want to find that vector there. And okay, so let's call that vector W, and let's call this vector W1. Now from previous knowledge, what is W1? W1 is essentially, the vector W1 is essentially the, it's the projection of the vector U onto the normal vector n, right? Essentially that's what it is. Now we are interested in the norm of this vector, because the norm of this vector is going to measure the distance between the point Q, the vertical distance between the point Q and the plane. Remember, there's the vertical distance. If you go down there onto the plane, that is the distance there that I'm looking at, and that distance there is the same as, remember, that distance of W1 there. So that is essentially the vector that I'm actually looking at. So what is W1 actually equal to? Remember, we said W1 is the vector. All right, so what is that vector according to my previous knowledge? It is the vector U dot product with the vector n divided by the norm of n, the vector n squared, right? Multiplied by, let's just fix that, multiplied by the vector n. Okay. So now it's just a straightforward application. So what is the dot product between U and n? So what is U? U is the vector. What did we say? It's x1 minus x0, y1 minus y0, z1 minus z0. Okay, so that is the vector dot product with n. Okay, and that I'm going to divide by the norm of the vector n, right, squared. Okay, so that's what the vector w1 is equal to. Okay, so what am I interested in? I'm interested in the distance. So I'm actually interested in the norm of the vector w1. So I want to calculate the norm of the vector w1. I want to calculate the norm of the vector w1. So what is the norm of the vector w1? It is the norm of, remember we said the vector u dot with n divided by the norm of n squared. Okay. Sorry, that's not correct. We are looking at the norm of that whole thing. Right, so that then becomes, according to my norm rules, that I treat as a constant, okay, and I multiply that with the norm of n, okay, and that then cancels, and you're left with the dot product between u, the absolute value of that, divided by the norm. Sorry, there's no squared there, it's already cancelled. Okay, so what is this term equal to? What is that term equal to? Well, we said u is the vector, it's basically the dot product between this vector here, x1 minus x0, y1 minus y0, z1 minus z0, okay, the dot product with n, which is ABC, okay, and you're going to divide that basically by the norm of n, which in this case is basically the square root of a squared plus b squared plus c squared. Okay, now carrying on from that, we get that is equal to, it's basically equal to a x1 plus b y1 plus c z1, right, minus a x0 plus b y0 plus c z0, okay, divided by the square root of a squared plus b squared plus c squared. Now if we go back to our plane equation, if I make x0 and I make y0 and I make z0, okay, that is then going to become, we can easily solve for d as negative that whole equation, right? All right, and that is then going to imply that our final formula for the distance is going to be equal to, it's going to be equal to ax1 plus b y1 plus c z1 plus d divided by the square root of a squared plus b squared plus c squared. Okay, so definitely this projection theorem has got some nice applications in as far as calculating distances between points and planes. Okay, let's look at the next problem. So they ask us to find the distance between that point and the line, straight line, but they tell us without using the formula derived from orthogonal projections. Now, the previous example we did was using orthogonal projections, and you can also use the previous example and do an analogous argument for the case where you look at a distance between a point and a straight line. We looked at the distance between a point and a plane. Now, so you're not allowed to use that. So how we would do this is, so you've got your straight line there, okay? This is the line y equals minus 4x plus 2. Okay, and what we want to do now is we want to look at this point. There's that point. All right, we want to look at that point there, and we'll call it the point P. And we want to find the distance between this straight line. So we want to find the distance. So we want to find that this point here, the point, call it x, and because it lies on the straight line, it has a y component of minus 4x plus 2. Okay, so that is the point. Let's call that the point Q. So that is this point here. It's this point here. Okay, right. Okay, now what I'm going to do is I'm going to pick a point on the straight line. Let's call that point, the point where x is 0 and then y is going to be 2. And we will call that point R. Okay, so now what I want to do is I want to find this distance. Okay, so I want to look at this vector, at the vector QP. Now the vector QP, we know from section 3.1 is 2 minus x, okay, and minus 5 plus 4x minus 2. That's the y component. So that is going to be 2 minus x. Let's just write that, minus 4x minus 7. Okay, so that's that vector. And now we want to look at this vector, that vector. Okay, and we call that vector QR. So QR is going to be the vector 0 minus x, okay, comma, 2 minus 4x plus 2. So it's 2 plus 4x minus 2. So that's the vector minus x, 4x. And now we have to solve for x, okay, because essentially what we want to do is we want to find the norm of this vector, of that vector. We want to find the norm of that vector. We can only find that once we have x, right? So now to get x is easy because this angle here is 90 degrees, okay? So we know that the dot product between two vectors that are orthogonal have a dot product of 0. So because we assume we want to find the value of x for which PQ is orthogonal to QR, that is going to imply that this vector here, dot product of this vector with the vector QP, must be 0, which is then definitely going to imply that this vector here, the vector 2 minus x, 4x minus 7, the dot product of that vector with this vector minus x 4x is going to be 0. Okay, and from there, it's now a straightforward little formula that we can, an equation that we can go and solve. So that's minus 2x plus x squared, okay, and that the other term is going to be plus 16x squared. This is just the dot product I'm calculating, minus 7 times 4x, which is going to be 28x. That's going to be 0, and therefore from there, if you work everything out, you're going to get 17x squared, okay, minus 30x is equal to 0. And that is just, you can solve that as x, 17x minus 30, which implies that either x is 0 or x is 30 over 17. Now, what solution are we looking at? We don't want x equals 0. We don't want x equals 0. So this is the solution we want. Okay, that's the solution we want. All right, so now we have the solution for x as 30 over 17. So now what is it that we want? We want the norm. We want the norm of the vector QP. So I want the norm of the vector QP. Okay, because that is the distance. If you go back, that's the distance. That is that distance there. That's that distance there. Okay, so we want the norm of that vector. So the norm of QP is going to be the square root of the x component squared plus the y component squared. Okay. Right, so that is going to be, that you can go and work out, that's the square root of 17x squared minus 60x plus 53. And if you go and plug in, for x, what did we say x was? It's 30 over 17. We get that is equal to, right, so that is equal to the square root of 53 minus 60, 30 over 17, okay, plus 17, 30 squared over 17 squared. Okay, and then basically that is going to be the square root of, you can go and work that out with your calculator, so that's 53 minus 1800 over 17 plus 30 squared, which is 900, divided by 17. And if you go and work that out, the square root of that is 0.24253 6. Well, that's more or less equal to units. Okay, so that's a nice application of orthogonality to find the distance between a point and a straight line. Okay, now this well-known result follows directly from orthogonality. If we have that, if we consider two vectors u and v that are orthogonal, then the norm of the sum of the two vectors, we know that that is the same as the dot product between the vector u plus v and itself. Okay, and this is very easy then to go back and note that that's u dot with u plus twice u dot with v plus v dot with itself, and we know v dot with itself again is the norm of u squared. Now we know that u and v are orthogonal, and this means that the angle between u and v is 90 degrees. Okay, and so that is going to just fall away. That's going to just fall away because those two vectors are given as orthogonal. So there's Pythagoras' theorem from orthogonality.